All right, we're going to run a t-test for the slope of the regression line. Remember what we're trying to do here. We are taking a sample slope from a sample data set that we gathered, and we came up with a prediction line. From that sample slope, we are trying to estimate what is the true slope of that regression line. That's what the confidence interval was doing. The previous problem told we're 90% confident that the true slope of the regression line lies between these two values. Now, what would we be doing with a test for the slope? What we're doing is testing to see if the line truly has a slope at all. Because if the slope of a line is zero, then it's completely useless in making predictions. If a line is completely horizontal, it doesn't matter what the x value is, the y value would always be the same. So we wouldn't have a useful line in predicting. So what we're going to test always for a inference for regression, always what we're going to test is there a slope? Maybe we think it's positive. Maybe we think the relationship or association is negative. Maybe we just want to see, is there a relationship? But the null hypothesis is always there is no difference. So in this case, the null hypothesis would be that beta sub 1 is equal to 0. And the alternative hypothesis could be several things. You're going to be really surprised. It could be greater than 0. It could be less than 0, or it could simply be not equal to 0. And we'll have to determine which alternative it is based off of the wording of the question and what the researcher is trying to look for. So in order to run a significance test, we need a test statistic. As we saw in the confidence interval, we use T star. So we know that for inference for regression, we're going to use T as our test statistic. So what is the test statistic? Well, it's B sub 1, the estimator, minus the hypothesized slope. Well, the null is always going to be 0. So it's going to be minus 0. Well, I'm not going to write minus 0 because I know if I subtract nothing, it doesn't change my answer. So really, that is the formula for the test statistic, but we're going to just look at it as B divided by the standard error of B. So let's put this to practice. Let's look at an example of this. We want to see if infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Child development researchers explored the relationship between crying infants 4 to 10 days old and their later IQ test scores. A snap of a rubber band on the sole of the foot caused the infants to cry. That's not cool. Okay. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the children's IQ at age 3 years using an IQ test. The table contains the data. Okay. So you can see all the data here. The computer output from the least square regression analysis of this data. Do these data provide convincing evidence at the alpha 0.05 level of a positive linear relationship between count of crying peaks and IQ? What a weird test. Snap the bottom of the baby's foot with a rubber band to see how they cry. Doesn't sound cool at all. All right, guess what? 4 steps. What's the first step? Know an alternative. What are we going to do? Okay, so we want the null is always there is no slope. The alternative, it says, is there convincing evidence that there is a positive linear relationship? So that means we want to test the alternative is B1 greater than 0 or beta sub 1. Okay, but we need to define the parameter. The parameter of interest here is beta. We're trying to find out the true slope of the regression line for all the data in the world. So all babies and IQs. Well, we can't snap every baby's foot with a rubber band and then test their IQ later. So we're going to use the small sample to try to answer the question about the larger population. What is B1? In this case, B1 is the slope of the regression line. It's the slope of the LSRL, the least square regression line, relating Y, which is IQ, to X, which is count of crying peaks. Okay. Step one, what are we going to do? That's what we're going to do. Step two, are we allowed to do this? Okay. Well, remember, we have to test linear. The scatter plot here shows a linear relationship. The data looks linear, so yeah, we're probably okay. Independent, you think there are more than 380 babies in the world? Yeah, we're safe there. Okay. Normality, well, the histogram here doesn't show any strong skewness or any outliers, so we're probably okay. Equal standard deviation, the residual plot shows a fairly equal amount of scatter about the horizontal line. Fairly equal amount of scatter here about the horizontal line, y equals 0. So equal standard deviation is somewhat okay. And then finally, random. Yeah, it says in the question that they randomly selected 38 infants or babies for this. So cool, we're good on conditions, we're allowed to do it. Okay. Now let's do the work. So our t-test statistic, as we saw on the previous page, t equals b sub 1 divided by the standard error of b sub 1. Well, we can get all of that from the computer printout. The slope is 1.4929 divided by the standard error of the slope, which is 0.48 whatever. Okay. 0.487. And when we do the work, we'll get 3.07. Uh-oh, why did I do the work? Look, 3.07 was given. The t-test statistic for the slope is given in the printout. I just wanted to show you how the formula worked and where that 3.07 came from. So we know the t-test statistic, and we should be able to figure out the degrees of freedom. Remember, for the inference for regression, there's always n minus 2 degrees of freedom. Since we abused 38 of these babies, 38 minus 2 is 36. So if I come to my t distribution table and I have 36 degrees of freedom and a t-test statistic of 3.07. Whoops, 36 isn't on the table. So we always go to the next smallest one, 30, and then I trap 3.07. 3.07 is between 0.0025 and 0.001. So based off of looking it up in the table, I can see that my p-value is between 0.0025 and 0.001, I believe. I need to go back and check that out. Yeah, it's larger than 0.0025, but it's smaller than 0.001. Well, I didn't need to do that because check it out. The computer printout gives me the p-value. The only thing I'm going to have to do is divide that p-value by 2 because the computer printout is giving me the p-value if the alternative was two-sided. So the p-value in this case is 0.002. Is that smaller than 0.05? Certainly is. Therefore, the data is statistically significant. I would reject the null and conclude that there is a positive linear relationship between crying peaks and IQ. Because this p-value is less than 0.05, then I would reject the null in favor of the alternative and say that there is a positive linear relationship between the count of crying peaks and the IQ in the population of